Okay. This class I have talk about how to implement this multi-rate conversion system, whether it is downsampling or upsampling. Okay. So now we talk about how to implement it. So so what I said, whether it is downsampling or upsampling, this side is nothing but a filter. So this filter is nothing but an FIR filter. If I say, then FIR filter can be implemented like this way, the delay. So FIR, what is FIR filter? Y of n is equal to summation of that AK into x of n minus k. So I know that convolution of filter coefficient along with that signal. So in Z domain, it is nothing but a Z to the power minus k. So if I want to implement using direct structure form, so I can say that x of m pass through a low pass filter which can be implemented using direct structure form. So let us say I said mth order filter, then I can say Z to the power minus m minus 1, that because m equals h0 is equal to 0, so h of m minus 1 multiply and add together. Then I downsample the signal and I get ym. So I can implement it in using a FIR low pass filter using a simple direct form structure. Now if you see that I can use, instead of after filtering, so this D downsample can be goes inside also. So I can say that instead of whole filter after downsampling, I can put this downsampling inside that direct structure. So what will happen? That means it will reduce the sum complexity. Okay. So that is the efficient implementation of direct form of the filter, or I can say dissemination filter. Similarly, or downsampling filter. Similarly, for interpolation or upsampling, that upsampling followed by a filter. Filter can be again implemented using a direct form structure. So it is nothing but a h0 z to the power minus 1. So delayed and then multiply and sum. This can be said that okay, instead of z in here, I can put the z in here also. So this is not there, so this will be there. So I can put the z here. So this is called transpose form of that implementation. So I can implement that FIR filter, whether it is HD or FIR filter after that upsampling or before the downsampling, which is called anti-aliasing filter, and after it called that removing of the multiple image of the signal. So both can be implemented using FIR filter. Now there is another example is there called multi-rate Nobel identity. Multi-rate Nobel identity. So if I say the dissemination, then a filter followed by a downsampling. So h of zd then followed by a downsampling. So if the xn signal is applied here, what is the V1z? V1z is nothing but a h of hzd in multiply by xz in z domain. So what is hyz? Yz is nothing but a V1 is the input and y is the output, and one d is the downsampling factor. So it is nothing but a 1 by d k equal to 0 to d minus 1 V1 z to the power 1 by d w di. What is w di? It is nothing but a e to the power j 2 pi by d into I. Okay. That we have already derived during the dissemination or downsampling. Now if I put this one in V1 value in this equation, so hd, so instead of this will become say z, so instead of hz I can say h of z to the power 1 by d, and zd was there d, so d cancel z, and w di into d, and x of z to the power 1 d w di. Z is equal to, I put z is equal to z to the power 1 by d w di. So since it is z to the power d is already exists, so it will be z into w d I d into x to the x of z to the power I 1 by d into w d I d. Now, since what is w d I d? It is nothing but e to the power j 2 pi by I d divided by d. D cancels, so e to the power j 2 pi I. So, I is an integer. So, I can say it is nothing but a 1 e to the power 2 pi cos 2 pi plus j sin 2 pi. So, once it is 2 pi, I equal to 1, I equal to 2, I equal to 3. So, every value it will be 1 because e to the power j 2 pi is nothing but a 1 to the power I is equal to 1, I is an integer. So, in that case I can say that yz is equal to 1 by d. So, this becomes 1. So, this becomes hz and this will be remain. Okay. So, what is hz? So, it is nothing but a hz into V2z. Let us consider this is an V2. So, I can say instead of first implementing anti-aliasing filter then downsample, I can downsample it and then pass through an anti-aliasing filter. Both will be same. So, suppose I have an 8 kilohertz signal, instead of passing it first FIR filter, which is band limited FIR filter, and then downsample, I can downsample it. Let us say I downsample by 2. So, first 8 kilohertz sampling rate converted to 4 kilohertz. Then I restricted the filter pi by d. It is nothing but a 2 kilohertz. I implement the 2 kilohertz filter. Output I will get 0 to 2 kilohertz only, which I desire. So, why we do the downsampling up? What is the advantage of doing the filter after downsampling? Because it can reduce the order of the filter. Since sampling rate is reduced, then the order of the filter can be reduced. So, multirate novel identity can be used for efficient computation. Similarly, for upsampling, let us say x of n. So, this is the upsampler, block diagram of an upsampler. So, I upsample, then remove that image, multiple image, keep the single image, and then I get the ym. So, if I do this block diagram, so what is V1z? V1z is nothing but a x of z to the power I. If it is upsampling by factor I, and then what is yz? Yz is V1 x. So, x of z to the power I is passes to the hzi. So, I can say hzi multiply by x of z to the power I. Now, consider I first do the filtering and then do the upsampling. So, what is first do the filtering? So, I can say V2z is nothing but a hz into xz. When it is passes to the upsampler, so it becomes V2z to the power I. So, I put z to the power I, hz to the power I, xz to the power I. So, this one and this one is same, yz's are same. So, this structure and this structure is same. This is called novel identity of interpolation or upsampling. So, why I required? So, if I place the filter before the upsampler means sampling frequency increases. So, my filter here I have to operate the filter at high frequency. Let us say I have a signal at 8 kilohertz and upsampling factor I equal to 3. So, I know hz has to be operated at 24 kilohertz, but in this case I can operate the filter at 8 kilohertz and filter output can be upsampled to factor 3. So, I can efficiently implement that filter. So, that is called multirate novel identity for interpolation. So, multirate novel identity for dissemination or downsampling, multirate novel identity for interpolation or upsampling. Both are exist. Okay. Now, I said efficient implementation of the dissemination. So, what is the problem? Interpolator or upsampling or downsampling? What are efficient implementation of upsampling and downsampling? So, what is the problem? So, when I say the upsampling or when I say the downsampling, let us say x of n is equal to 1, 2, 3, 4. Now, if I say downsample by factor 2, d is equal to 2, that what we select? We select sample number 1, sample number 0, then discard the sample number 1 and we select sample number 3. So, xn, so y of n, I can say that it is nothing but a 1, 3 and 4 will be discarded and 5 will be selected. So, when I say the filtering, so after downsampling or after upsampling, when I want to implement the filter, so what I am doing? Basically, that discarded sample is also included my computation if I implement the filter. So, why should I include that coefficient during filtering? Because it reduces the order of the convolution. What is the convolution? The complexity of the convolution depends on the length of the signal. Now, due to the downsampling, length of the signal is reduced. So, why should I use that whole length of the signal for filtering? So, how can I efficiently implement the filter that those samples which I am discarding I will not use? Similarly, in case of upsampling, let us say upsampling factor by 2, then what will happen? In between 1 and 2, I put a 0. Now, when I multiply convolution, x of n multiply by the filter coefficient, if the x of n value is 0, then why should I include that part in the convolution? So, both the cases, I want an efficient algorithm by which I can say that in case of interpolation for sample value x of 0, the filter convolution will be not happened. And in case of downsampling, the sample which I am discarding, I should not want to compute that value. So, to implement that, there is a concept called polyphase filtering. So, we can say that efficient structure of interpolation and deviation in terms of computational complexity can be formed using polyphase filtering. First, I have to understand what is polyphase filtering and how this polyphase filtering can reduce the computational complexity or the redundant calculation which exists in case of upsampling and downsampling. So, what is polyphase implementation? So, let us say I have a filter x of n passes through an FIR filter and then downsample by 2. Let us say this is my system diagram. So, what I said, output only produced for even sample, computation of the odd sample are not taken, because I know I will take x of 0, then I will take x of 2, not x of 1, because x of 1 I am discarding, it is downsample by 2. So, for even sample, output are produced, for odd sample, output are not produced. So, let us say write down that mathematical form. So, I can say yz by xz, which is the filter is called hz, is nothing but a 1 plus z to the power 1, h0, if the h0 is equal to 1, then I can say it is 1 into h1 into xz to the power minus 1, or I can write h0 also here. So, here will be h0. Okay. So, now if you see that h1 z to the power minus 1, h2 z to the power minus 2, h3 z to the power minus 3. So, when I say in time domain, yn is nothing but a x of n multiplied by h0, h1 is multiplied by x of n minus 1 delayed by 1 sample, delayed by 2 sample, delayed by 3 sample, dot dot dot. If the order of the filter is m, so last coefficient is h of m minus 1, x of n minus m minus 1. Okay. Now, what is yn plus 1? I increase, instead of n, I write n plus 1. So, x of n plus 1. So, x n is replaced by n plus 1. So, h1 into 1 minus 1. So, xn, then x of then 1 will be reduced, n minus 1, n minus 2. So what is n plus 2? X of n plus 2 h1 into x of n plus 1 h2 into xn, like that. Now I can say, if I select only y even part, so if you say y even is equal to h even multiplied by x even plus h odd multiplied by x odd. Let us say that, let us n equal to, let us say 1, n equal to 1. So y2, so this one is nothing but a h0, or I can say h0 is equal to 1, then x2 plus, I can say this one, n equal to 1. So x2 plus h1 into x1 plus this line I am writing. So h2 into x of 0. So 1 minus the x of 0 plus h of 3 into x of minus 1 plus h of 4 into x of, I can say, n minus 3. So that is minus 2. So if you see h2 x0, h4 x2 and x1 h1, h3 x minus 1. So I can say that y even is nothing but a h even multiplied by x even plus h odd multiplied by x odd. Similarly, y odd is nothing but a h even multiplied by x odd and h odd multiplied by x even. So check it. Let us say for y equal to 1, n equal to 1. So y1 is equal to xn, x1, h1, x0. So h becomes odd, x becomes even. So that is why even h odd, x even, and if it is h even, then x become odd. Now for d equal to 2, this y odd I not required. I only have to calculate y even, because y odd is not exist, because I know x of n, when it is downsampled by 2, that means y of n is equal to x of 2n, elsewhere it is 0. So it is either 0, 2, 4, all those exist. So I can say y even exist, y odd is not exist. Now if I say this is the y even, y2n, so it is exist 2k, 2n minus 2k, and this is odd, 2k plus 1 is odd. So it is nothing but a 2 into n, 2n minus 2k plus minus 1. So that is this one. So I can say yz is equal to h of 2k z to xz. This is nothing but a xz z to the power minus 2k. Similarly, this is nothing but a xz z to the power minus 2k minus 1. Now if I say the minus 1 is outside, so I can say that, or I can simplify this, so minus 1 is outside. So this is nothing but a, I can say h, this term will be there, and h z to the power minus 1 will be there, and then z to the power minus 2k. So I can say, this is an filter, and this is also an filter. So this is p0z and this is p1z square, because 2k z to the power minus 2k is nothing but a z to the power square to the power minus k. So k varies from minus m into infinity. So I can say it is p0z square, it is p1z square delayed by z to the power minus 1. So I can say HPZ can be synthesized by two polyphase filter, which is delayed by one sample. That is why it is called polyphase. Okay. So if I want to put it generalized form, let us say Hz, this is my FIR filter. Okay. So now Hz is equal to, so I can break it even and odd term. So when I break it even and odd term, it is nothing but a p0z square in plus z to the power minus 1 p1z square. So this is called two-phase decomposition. Now let's say I want to m-phase decomposition. I want to decompose it H0, Hz in a m number of phase. So if you see two phase, odd and even, so I can say k, index k is divided by m number of sample. So it is km, then km plus 1, then km plus 2 plus 2, like that, then km plus 3, like that. So m number of decomposition is happen. So last one is km plus m minus 1. Okay. So which is nothing but a z to the power m minus 1 into z to the power mk. So I can say that this is nothing but a polyphase P0 z to the power m. This is nothing but a delay by P1 z to the power m. If you see, why it is P0? Because it is 0th one. Why it is P1? Because it is 1. So that's why it is so second term P1, third term P2. Similarly, mth term will be Pm minus 1. So if I write down in summation form, so I can say I equal to 0 to m minus 1, it is z to the power minus I pi z to the power m. So if I derived it, what will happen? That I equal to 0, z to the power minus 0 p0 z to the power m plus z to the power minus 1 p1 z to the power m. So dot 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 dot. So this is my polyphase decomposition of a filter Hz. So m phase, poly means more than one, m phase decomposition. So now if I want to implement the filter, what is the signal flow diagram of the filter? So let's say I have a three phase, so Hz is equal to three phase decomposition. I equal to 0 to 3 minus 1 z to the power minus I pi z to the power m. M is equal to 3. So there will be a zq. Okay. So I can say Hz is nothing but a z to the power minus 0 p0 zq plus z to the power minus 1 p1 zq plus z to the power minus 2 p2 zq. So how do I implement x of n? So this is x of, so this is my h of z. So how do I implement? That p0 z will directly pass. The z to the power 0 is nothing but a 1, and then delayed by one sample z to the power minus 1, I implement p1 z, done. Then z to the power minus 2, why it is coming? Because I know yz is equal to hz into xz. So I can say it is nothing but a p0 z to the power q plus z to the power minus 1 p1 z plus z to the power minus 2 p2 z q whole multiply by xz. So it is nothing but a p0 zq plus xz z to the power minus 1. That means sample x will be delayed by one sample. So that's why I delayed by one sample. Some x will be delayed by two sample. So z to the power minus 1, z to the power minus 1, delayed by two sample. So some two sample delayed signal will pass through p3zq. One sample delay is p1zq, and now no delay is p0zq. All are add together, I get yn. So this is called polyphase structure for m is equal to 3. Similarly, let us say m equal to 2. This one. Okay. So this is a disseminator. Dissemination factor d is equal to 2. So I decomposite that filter in two polyphase form, and then I disseminated by factor 2. That means this filter will not use that discarded sample. So, this will be z square, sorry. Okay. Similarly, for now dissemination can be that if I use the Nobel identity here, so filter then downsampling. Nobel identity they said that allow me that first downsample the signal and then filter. So, I use that Nobel identity, first downsampling then filtering. So, first downsampling and then filtering I can do that one also. So, how do I do that? First downsampling this side, sorry there is a mistake. So, this side I will first downsampling and then I implement that filter. Both are possible, first downsample and then filter. Similarly, for interpolation, upsampling and filter, Hz is implemented like this way, for using polyphase filtering. Okay. Now, I can use the again Nobel identity, first filter, first I can say the filter and then, sorry this will be not, this will be I or I, so I can say that first filter then I, but I can be included inside also, then delay, no problem. So, using Nobel identity I can change the structure of the filter, but polyphase implementation is mandatory. Okay. Now, there is another problem, that is called sampling rate conversion by stage. That instead of single, let us say this is a single stage sampling rate conversion. This is a single stage single stage sampling rate conversion. So, downsample by factor D in a single stage. I can say that D is nothing but a product of many D. Let us say D is nothing but a product of Di. So, for example, let us say D equal to 50, it is a product of 2 into 25, or let us say D equal to 100, D equal to let us say 25, I can say it is a product of 5 into 5. So, instead of single dissemination, I can say that signal first disseminated by D1. So, D is a product, D is equal to D1 into D2. So, in this case, let us say D1 is equal to 25, D2 is equal to 2. So, first I downsample by D1, again I downsample by 2, factor 2, then ultimately total downsampling is 50. So, instead of single stage, I can use multiple stage for downsampling. So, overall dissemination is D1 multiplied by D2. This can be done. Okay. Why we do that? That is also an important factor. Similarly, for interpolation also, that I can, instead of single interpolation, I can say that upsampling by, let us say upsample I is equal to let us say 50. So, first upsample by 25, then upsample by 2, possible. So, multi-stage sampling rate conversion. So, why we use multi-stage? What is the advantage of using multi-stage? The advantage is reduce of computation. I will show you. So, if in a single stage, if I want to implement the filter and then single stage 50, I can show you that order of the filter, and then instead of single stage I can use multi-stage and then dissemination by D, then I will show you the order of the filter. So, it reduces computation, because second stage I am computing using a lower sampling rate. Since the filter number of filter coefficient is reduced, then the finite word length problem is solved. Then what is the disadvantage? Many times, let us say D is equal to 13. Can I process in multi-stage? No. I cannot do that. So, let us say I is equal to 5, I cannot do that, I is equal to 19. So, if that dissemination interpolation ratio cannot always be easily factorized in a suitable number, then I cannot use multi-stage dissemination or multi-stage interpolation. Then every time the problem is aliasing, passband aliasing. So, there is a problem in passband aliasing will happen, because multi-stage multi-aliasing filter will be there and passband aliasing, every time there will be aliasing effect will be there. So, that is the disadvantage part, but advantage is maximum. So, if I design the filter such a way that aliasing is not allowed, so this portion I can remove, but if the D and I is a factor something which cannot be decomposite, I cannot use multi-stage decomposition or multi-stage interpolation. But yes, there is a definite advantage to use multi-stage decomposition or multi-stage upsampling or downsampling. So, what is that? So, multi-stage means I am using two stage, it may be a n number of stage, Z1, D1, Z2, D2, Z3, D3, like that way. So, there is nothing called that I have to restrict it. So, D can be, let us say D is equal to 100, I can say D is equal to D1, that means 5 into 4 into, let us say 5 into 5 into 4, may be possible, 5 and 4 or 25 into 4. So, multi-stage, if the D is permitted to decomposition, if I decompose it, then the order of the filter will be lowered down. So, next class I will give you the example how the order of the filter is lowering down and that advantage is taken. Okay? Thank you.